Hello, and welcome to this video lecture on section 2.6, Variation and Applications. The learning goals for this section are to find equations of direct variation, inverse variation, and combined variation given values of the variables, and also to solve applied problems that involve variation. So we're going to extend our study of formulas and functions by considering applications that involve a mathematical process known as variation. And there are different types of variations that we will be discussing in this section. We begin with those problems that involve a direct variation between two variables. As an example of a direct variation that you're probably familiar with, your hourly wage, if you have a job and you're being paid on an hourly basis, is a set amount, and the amount of money in your paycheck will depend on how many hours you work. Here in this example, the median hourly wage for an elevator and escalator installer / repairer is $35 per hour. That means that if they do a job and they work for 1 hour, they get paid $35. If they work 2 hours, they get paid $70. In 3 hours, it becomes $105, and so on. And so you can generate a series of ordered pairs in which the number of hours worked represents your first coordinate, the x variable, and the amount you get paid represents the second coordinate, the y variable. And that the ratio of the second coordinate to the first coordinate will be the same for each pair of numbers. 35 divided by 1 is the same as 70 divided by 2, is the same as 105 divided by 3, is the same as 140 divided by 4, and so on. In all four cases here, that ratio will equal 35 because you're being paid $35 per hour. So here we see the plot showing how much you earn based on how many hours you work. Now, whenever a situation produces pairs of numbers in which the ratio is constant like this, we say that we have a direct variation. And in this case, the amount earned, E, will vary directly with the number of hours worked, T, where E divided by T will equal this constant 35. We can express that as well as E is equal to 35 times T. So in this sense, we can define a function that is the earnings that depends on the time worked T. And this is the general form of an equation of direct variation. In this particular example, the coefficient 35 is known as the variation constant, and it happens to represent the rate of change of earnings with respect to time. So we define direct variation as follows. If a situation gives rise to a linear function, f of x equals some number k times x, or equivalently y equals k times x, where k represents a positive constant, we say that we have a direct variation, or that y varies directly as x, or that y is directly proportional to x. The number k in this equation is called the variation constant, or occasionally it's referred to as the constant of proportionality. So in example 1, we are asked to find the variation constant as well as an equation of variation in which y varies directly as x and y equals 32 when x is equal to 2. So that means we have two pieces of information that we can use to solve this problem. First, we know that y varies directly as x, and we also know that when x is 2, y is 32, so an ordered pair of 2, 32 would be a point on the line that represents this variation equation. The equation y equals kx, we can substitute the given values of x and y. We get 32 equals k times 2, we divide both sides by 2, and we find the value of the constant k is equal to 16. Once we know that value, we can then substitute that back into the general equation of variation, and we get y is equal to 16x. So the variation constant is k equals 16, and the equation is y equals 16x. We'll go ahead and do exercise number 1 now. In this exercise, we are told that y varies directly as x, and that y equals 54 when x is equal to 12. So all of these variation type problems will begin by you writing out the general form of that particular type of variation. For a direct variation, you always will start with this, y equals kx. Then you'll take the numbers given in this problem for x and y and substitute them in to figure out the value of the constant k. So we have y equals 54 when x is equal to 12. To solve for k, we divide both sides by 12. And we get 54 divided by 12. We can simplify that because they both have a common factor of 6 in them. 54 would be 6 times 9, and 12 would be 6 times 2. I'm just doing this explicitly to remind you how to simplify a fraction. The 6's divide out to be just 1, and we get our constant k equals 9/2. Or if they ask for it in decimal form, which they may choose to do, you would replace it with 4.5. Once we have that value, we then go back to the general form of the equation and substitute in for k, and we get y equals 9/2 x. And that would be the equation of variation for this particular situation. Continuing on, this next example involves measuring the amount of water you get when snow melts. The number of centimeters of water W produced from melting snow will vary directly as S, which is the number of centimeters of snow. Meteorologists have found that under certain conditions, 150 centimeters of snow will melt to leave you with 16.8 centimeters of water. So to how many centimeters of water will 200 centimeters of snow melt under the same conditions? So in this problem, we can express the amount of water as a function of the amount of snow. And here you can use letters that are appropriate for the problem. So W of S, the amount of water based on the amount of snow, will equal some constant K times S, because the amount of water produced from melting the snow will vary directly as the amount of snow as shown here. We plug in the given numbers that you get 150 centimeters of snow. That turns into 16.8 centimeters of water. And so W of 150 is equal to K times 150. And that value is equal to 16.8 centimeters. And then dividing both sides by 150, you would find that the constant K is equal to 0.112. Once we know that constant, we can substitute it back into our function, and we get our equation of variation is W of S equals 0.112 times S. Graphically, we could plot that as a linear function shown here with a y-intercept of 0. The second half of the problem then is what is the value of W when S equals 200. So we want to know how many centimeters of water will 200 centimeters of snow melt under the same conditions. So we substitute S equals 200 into our function and multiply that by 0.112, and we would find that you would get 22.4 centimeters of water under those circumstances. This next example, number 17, asks the maximum number of grams of fat that should be in a diet varies directly as a person's weight. A person weighing 120 pounds should consume no more than 60 grams of fat per day. what would be the maximum daily fat intake for a person that weighs 180 pounds. So once again, this is a direct variation. As it says, the number of grams of fat varies directly as a person's weight. So we will define this as F of W equals a constant times W, constant K. So the number of grams of fat will depend on the weight. We plug in the numbers that we are given. 120 pounds for your weight leads to 60 grams of fat. Don't be too concerned about the units in this case, just plug in the numbers. So 60 grams of fat equals K times 120 pounds. Divide both sides by 120, and we get that the constant 60 over 120 is 1/2. So now, once we know the constant, we can now define the function f of w equals 1/2 w. We understand that the value for f represents grams of fat, and the value for w represents pounds of weight. We were asked what is the maximum daily fat intake for a person that weighs 180 pounds. So we evaluate the function when w equals 180. And that's 1/2 times 180. 1/2 times 180 is equal to 90. So f of 180 will equal 90 grams of fat. And that is the answer to the question that is posed in this problem. So those were examples of direct variation. Another type of variation is known as an inverse variation. Here we see, for example, suppose that a bus is traveling a distance of 20 miles. If the bus travels at a speed of 5 miles per hour, the trip will take 4 hours. When they go 10 miles per hour, it will take 2 hours. At 20 miles per hour, it takes 1 hour. And at 40 miles per hour, it will take 1/2 of an hour, and so on. You can plot those values as ordered pairs on a graph, using your speed as your x or first coordinate, and the amount of time in hours as your second coordinate to get your ordered pairs. And in this instance, it's not the ratio that is a constant, it is the product. If you multiply the two numbers, 5 times 4, 10 times 2, 20 times 1, and 40 times 1/2, that number will be a constant. In this case, it will equal 20, which as it happens is the distance that was traveled. So here we have a situation in which pairs of numbers, when you multiply them together, will produce a constant value. And we refer to that as an inverse variation. In this case, the time it takes to travel will vary inversely as the speed or the rate. So r times t will equal your constant 20. Or equivalently, the time t will equal 20 divided by r. So we could define our function for the time in hours, t of r, is equal to 20 over r. And this is the typical form of an equation of an inverse variation. And again, the coefficient 20 in this problem is referred to as the variation constant. And notice that unlike with a direct variation, whereas one value goes up, the other one goes up as well. Here, as one value increases, the other value will decrease. So we can define an inverse variation as follows. If a situation gives rise to a function f of x equals some number k divided by x, or y equals k divided by x, where again, k represents a positive constant, we can say that we have an inverse variation, or that y varies inversely as x, or that y is inversely proportional to x. The number k is called the variation constant, or the constant of proportionality. Here in example 3, we are asked to find the variation constant and an equation of variation in which y varies inversely as x, and y will equal 16 when x is equal to 0.3. So an ordered pair of 0.3, 16 represents a solution to the equation y equals k divided by x. So we again substitute the values. 16 equals k divided by 0.3. We multiply both sides by that denominator of 0.3, and we get our constant k would equal 4.8. So in this particular problem, the equation of variation becomes y equals 4.8 divided by x. And the graph of that particular equation is shown over here to the right. We'll now go ahead and work on exercise number 3. Here we're given that y varies inversely as x, and that y will equal 3 when x is equal to 12. So again, in these sorts of problems, you always start with the general form of an equation. For an inverse variation, that general form will be y equals k divided by x. From there, we then substitute the values we are given for x and y in order to figure out the value for k, and then from that we can get the actual specific equation of variation for this particular problem. So y equals 3 when x equals 12. So we get 3 is equal to k divided by 12. We multiply both sides times 12, and that gives us k is equal to 36, 3 times 12. That's our constant of proportionality, and our equation of variation then is just y equals 36 divided by x. And that would be the answer to this particular problem. So there are a number of real-world situations that can translate to an equation with an inverse variation, such as example 4 here, in which we're trying to figure out how much time it will take to fill a swimming pool. The time t required to fill a swimming pool will vary inversely as the rate of flow r of water into the pool. A tank truck can fill a pool in 90 minutes at a rate of 1,500 liters per minute. How long would it take to fill the pool at a rate of 1,800 liters per minute? We can express the amount of time required as a function of the rate of flow. So time as a function of rate equals k divided by r because it varies inversely with that rate. So we first have to evaluate that to determine the constant k, and then answer the question about how long it would take to fill it at a different rate. So we use the given numbers that it takes 90 minutes to fill it at a rate of 1,500 liters per minute. So the time is 90, the rate is 1,500. We solve for k by multiplying both sides by 1,500, and our value for the constant becomes 135,000. And then we have our equation of variation. That will be t of r equals 135,000 divided by r. Next, we can use that equation to find how long it would take to fill it at a rate of 1,800 liters per minute by substituting 1,800 in for r and evaluating that ratio, and we would find it would take 75 minutes. So the answer to the question is that at the rate of 1,800 liters per minute, it would take the tank truck 75 minutes to fill up the pool. So we'll go ahead and do exercise 15 next. Here we have the time t required to drive a fixed distance will vary inversely as the speed r. It takes 5 hours at a speed of 80 kilometers per hour to drive a fixed distance. The question is, how long will it take to drive the same distance at a speed of 70 kilometers per hour? Note, in a problem like this, it's sometimes beneficial to think about whether your answer should be bigger or smaller than the values that were given in the problem already. If you're going slower, it should take longer in this particular problem, is the basic thought here. So your answer should be greater than 5 hours. But we begin by noting that the time t will equal some constant divided by the rate r. The time required to drive that distance will vary inversely as the speed r. So that's your inverse variation. It takes 5 hours at a speed of 80 kilometers per hour to drive that distance. And so we express that as 5 equals k divided by 80. We multiply both sides by 80, and we get that the constant k is going to equal 400. So our equation, therefore, is actually t equals 400 divided by r. And we can use this equation to answer the question of how long it will take to drive the distance at a speed of 70 kilometers per hour. So we substitute 70 in. We get t equals 400 divided by 70. This one we'll use a calculator for, so 400 divided by 70 will give us about 5.7 hours. And that would be our answer. So summarizing the procedure for solving either a direct variation or an inverse variation problem, first determine what kind of variation you're dealing with. Is it a direct variation or is it an inverse variation? Then write the equation out in the form y equals kx if it's a direct variation, or y equals k divided by x if it's an inverse variation. Take the numbers given in the problem that are known and substitute for x and y. Use those to determine what the value is for the constant k, and then write out the equation of variation with that value for k. And if asked, use it to find the values of unknown quantities in the problem. So besides direct variation and inverse variation, there are two other types of variations that we want to look at. First, we'll look at the problem of a direct variation or an inverse variation, where y varies directly as the nth power of x, or varies inversely as the nth power of x. In each case, you are told that there's a direct or an inverse variation, and that it varies as the square of x, or the cube of x, or the 10th power of x, or whatever it happens to be. In that case, you start with the equation y equals k times x to the n if it's a direct variation with an nth power, or y equals k divided by x to the n if it's an inverse variation to the nth power. Alternatively, you can also be asked to evaluate a variation problem where y varies jointly as two or more different quantities, such as x and z. If it's jointly, that's assumed to be a direct variation. If it says jointly and inversely, the inverse part is in the denominator and the jointly part is in the numerator. So other examples of combined variations include the following formulas. The volume of a shape called a right circular cylinder, V equals pi r squared h. Here the volume, the radius r, and the height h are variables, while pi represents our constant. We could therefore say that V varies jointly as h and the square of r, and in that formula, k would equal pi, the variation constant. Here in example 5, we are asked to find an equation of variation in which y varies directly as the square of x, and y will equal 12 when x is equal to 2. In this particular example, we start out with the direct variation, but as the square of x, so y equals k times x squared. You take the values given, y equals 12 and x equals 2, and substitute them in. 2 squared equals 4, and we solve that for k, and we get that the constant equals 3, and therefore our equation is y equals 3x squared. And that would be the answer to this example. We'll go ahead and do exercise 27 next. In this problem, we are told that y varies directly as the square of x, and y equals 0.15 when x equals 0.1. So again, we start with the general form of the direct variation with the square of x. So y equals kx squared. We substitute the numbers that are provided for both x and y. So y equals 0.15 equals k times x, which is 0.1 squared. We evaluate 0.1 squared as 0.1 times 0.1. That will be 0.01 times k. And we either multiply both sides by 100 or divide both sides by 0.01. We'll do that part. You'll get the same result either way. And you'll find that k will equal 15. And so our equation then is simply going to be y equals 15x squared. And that will be the answer to this particular problem. Here in example 6, we are asked to find an equation of variation in which y varies jointly as x and z, and where y equals 42 when x equals 2 and z equals 3. So a joint variation, we start with the equation y equals k times x times z. Again, jointly in this context is a direct variation, but with more than one variable. We substitute the values that are given, y equals 42, x equals 2, z equals 3. We get 42 equals k times 6. Divide both sides by 6, and you find that k will equal 7. And therefore, your equation is y equals 7xz. We'll now go on and do exercise 29. In this exercise, we are told that y varies jointly as x and z, and y equals 56 when x equals 7 and z equals 8. So again, we need to set it up properly. Y equals kxz. We substitute the values that were given. Y equals 56 when x is equal to 7 and z is equal to 8. So we get 56 equals k times 56. We divide both sides by 56, and we find in this example the constant k will equal 1, and therefore the equation is y equals xz. And that would be the answer to problem number 29. So we can further extend these ideas. In example 7, we are told to find an equation of variation in which y varies jointly as x and z and inversely as the square of w. And y will equal 105 when x equals 3, z equals 20, and w equals 2. So we start by writing out the general equation of variation. Y is equal to a constant. It varies jointly as x and z, so a constant times xz, and it varies inversely as the square of w, so divided by w squared. It's important to know how to write this equation to start the problem, and then you can substitute your values for the different variables. Y is 105, x is 3, z is 20, and w is 2. You get 105 equals k times 60 divided by 4 is 15. Divide both sides by 15, you get a constant equal to 7. And therefore, your equation of variation is y equals 7xz over w squared. We'll do exercise 33 next. In this exercise, we are told that y varies jointly as x and z and inversely as the product of w and p. And that y will equal 3/28 when x equals 3, z equals 10, w equals 7, and p equals 8. So again, the first thing we need to do is to write our equation of variation. So the equation of variation here is y equals k. There's always a k in the numerator to figure out. Jointly as x and z, so x times z is in the numerator. And inversely as the product of w and p, inversely means in the denominator. And so that is the general form of the equation of variation that we start for this problem. Next, we substitute the values that were given. y equals 3/28. We do not yet know k. The whole purpose is to figure out that constant. X equals 3, z equals 10, w equals 7, and p equals 8. We then evaluate the quantity on the right side. We have 3/28 on the left side. We get 30 over 56. To solve for k, we want to multiply both sides by the reciprocal of that 30 over 56. So 56 over 30, 56 over 30. And you can plug that into a calculator and try and simplify it from there. But the easier way to do this is to recognize, because you're multiplying these things, that 56 divided by 28 is just 2 over 1. So we could substitute 2 over 1 for those two. And 3 divided by 30 is 1 over 10. So that becomes a 1, and that becomes a 10. And of course, on the right-hand side, the 30 in the numerator divides out the 30 in that denominator, leaves you with just 1. And the 56 in the 56 divide out and leave you with 1. So you get k equals 2 times 1 over 10 times 1. 2/10 simplifies to 1/5. So our equation of variation, therefore, becomes y equals 1/5 xz divided by wp, but we'll write it as xz over 5 wp, just incorporating the 1/5 into that denominator. And that would be our equation of variation for this particular situation. So we'll finish out this section in this video by doing another applied problem that we can model with equations of combined variation. Example 8 involves calculating the volume of a tree. The volume of wood V in a tree will vary jointly as the height of the tree and the square of the girth, which is basically the distance around the tree, which you can think of as being the perimeter or the circumference of the tree. If the volume of a redwood tree is 216 cubic meters when the height is 30 meters and the girth is 1.5 meters, what is the height of a tree whose volume is 344 cubic meters and whose girth is 1.6 meters? So the first thing you want to do is find the value of k by using the information for the particular type of variation. We are told the volume V varies jointly as the height h and the square of the girth g. So V equals some constant k times h times g squared. This is what we have to start with. If you don't get that, you will not get these problems correct. We then plug in the numbers that are given in the problem, that the volume is 216 cubic meters when the height is 30 and the girth is 1.5. Going through the process of evaluating the constant, you get 30 times 2.25, 67.5. You divide that into 216, and you find that your constant is 3.2. So our equation of variation is V equals 3.2 times hg squared. We then take the numbers in the second part of the problem, a volume of 344 cubic meters and a girth of 1.6 meters, plug those in, and we estimate the height of the tree. The numbers here suggest the height to the nearest meter is 42 meters. And so we'll finish out the video with our final exercise, number 35, the intensity of light. In this exercise, we are told that the intensity I of light coming from a light bulb will vary inversely as the square of the distance d from the bulb. Suppose that the intensity is 90 watts per square meter when the distance is 5 meters. We are asked the question, how much farther would it be to a point where the intensity is 40 watts per square meter? This is a little bit different from these other problems because we're not asked how far it would be from the light bulb. We're asked how much further from that distance of 5 meters. So I will begin by drawing a little picture here. where we have our light bulb shining in all different directions. And at 5 meters away, our intensity is 90 watts per square meter. The question is how much further will it be for the intensity to be 40 watts per square meter? So it's going to be a two-part process. We first have to figure out the constant K for the problem, and then from that figure out how far from the light bulb you need to be to have that intensity. But then we take that distance from the light bulb and we subtract 5 meters because it's how much further you need to be. So for the first part, we have that the intensity varies inversely as the square of the distance. Varies inversely as the square of the distance d. So that's our equation. We are told that the intensity is 90 when the distance is 5. So we write the denominator as 25, 5 squared. K equals 90 times 25. And you can either do this in your head or with a calculator, but it should equal, let's see, 2250, I believe. But 90 times 25 is 2250. Next, we are asked to determine how far away the intensity will be 40 watts per square meter. So our equation I equals 2250 divided by d squared. We're told the intensity is 40. We have to solve for the distance d. So we have 40 equals 2250 divided by d squared. We can multiply both sides by d squared and divide both sides by 40 times d squared over 40 times d squared over 40. So on the right side, the d squareds will cancel out. On the left side, the 40s will cancel out. And we get d squared equals 2250 divided by 40. And 2250 divided by 40 is 56.25. To find the distance, however, we have to take the square root of both sides. And that gives us a distance, so we use the square root button here, of 7.5 meters. Now that's the distance from the light bulb. But the problem, as a reminder, asked us how much farther than 5 meters would we have to be for the intensity to be 40 watts per square meter. So the additional distance, if this distance here now is 7.5 meters from the light bulb, the distance of interest, d, is going to be 7.5 minus 5, or 2.5 meters. And that would be the answer to this particular question. And so with that, that will conclude our video lecture on section 2.6. And as a reminder, the homework and quizzes for these remaining sections from chapter 2 are all due in my lab by midnight Monday night.